Hey, what's up, guys? I know it's been a while since I last posted. Just been experimenting with some different recording softwares. I think this one will be a lot better and the videos come out more crisp. But yeah, let's begin this leak code problem. So this leak code problem is to find the minimum cost to cut a stick. And I came across this problem yesterday. And although the description is kind of hard to understand, the problem itself is pretty easy to code. So essentially, we're given a wooden stick of length n, and it's kind of like a ruler stick. So it has these positions. It has these positions on them. Along with this, we're given an integer array called cuts, where cuts at I denotes the position you can perform a cut. And it actually makes a lot more sense if you take a look at the example here I have on the right. So let me just move the screen over. So in this example, we're given a ruler stick of length 7, as you can tell from the marking. And here we're given a cuts array with the following positions we can make a cut at. If we run through the problem, it's really simple. Let's just go through it in order. So at position 3, we do our first cut. When we do this cut, the total length of the ruler stick, total length of this is initially 7. So we're going to add 7 to our output. After we do that cut, we're left with two different ruler sticks. But we still need to go through the remaining array and perform all those cuts. On the left, we don't really have a choice on where we can make the cut since there's only one option. On the right, however, we have a choice of making the cut at 4 or 5, and this changes our total output at the end. So if we choose to make a cut at position 5 here, notice that the length of this ruler stick is only 4. So we're going to add that to the output. Now, once again, we've split the ruler, so we have two different choices. Really only the choice on the left matters. And now we need to do our remaining cut. One at position 1, which is of length 3, so we're going to add that. And then finally, a cut at position 4, which is of length 2, so we're going to go ahead and add that. If you add all of this up, this equals 16, which is the output we should return, a different output. Okay, let's work through the brute force solution. So I kept the example we just did on the screen because I think it makes it a little easier to understand how the brute force solution works. So in this example on the left, we really started by cutting initially at position 3, but we could have easily also started at position 1 or position 4 or position 5, and each of these positions can significantly impact the output cost. So you can already see that we could have honestly had C branches, uh, choosing to start our initial cut at any one of the given positions. After this, once again, over here we chose to do our next cut at position 5, but again, we could have chosen to do it at 4 or even 1, and it could have also changed our output. So now we only had C minus 1 positions to choose from. And if you go another branch down, you'll have C minus 2 positions to choose from. So essentially for the brute force solution, you need to try every single combination to find that minimum cost to return. Now, although this is pretty inefficient, it's actually pretty easy to code up because this is essentially a depth first search solution where we try every single combination. If we were to calculate the time complexity of this, um, so the number of branches we have at each point is basically C. If C branches, the total height of the tree will also be C because we need to use up every single uh, every single number in the cuts array. And although it's not obvious here, but creating these branches will also require a loop within the DFS. So the total time complexity for this will actually be C times C to the C. If we want to calculate the space complexity, I'm pretty sure it's only O of C because this is like a stack. So if we start at position 3, then we go to position 5, we add it to the stack, we add this to the stack, we add this to the stack, we pop it from the stack, we pop it from the stack, we try this one, we pop it. Eventually the the total number of values the stack will hold is still O of C. Now, one lingering question you might still have is, after each cut, how do we make it so that the proper cut is done on the correct ruler stick length? So for example, uh, over here, when we made this cut at 3, we essentially had 2 different ruler sticks. In code, this is essentially 2 different branches. And because we're going to keep track of the start and end pointer of each stick, this is going to dictate the current length of the ruler stick. And so when we make that cut, we can essentially take the difference between these two and add that to our output. That way we can also avoid doing improper cuts, because if we try to make a cut of size 5 on a ruler stick that is only of length 3, that shouldn't be possible. Okay, let's work through it on LeetCode. So let's first create our helper function, which I'm just going to name DFS. So the only 2 parameters we're passing to this is the start and end pointer for our ruler stick. We can initialize this down here. So our start of our stick is position 0 and the end of our stick is n. Now, because we're going to be returning the output cost, let's create a output array, a variable, and set it equal to float infinite. We want it to be a large number because we're trying to return the minimum. Now let's go through the cuts inside of cuts to make sure we're doing the proper cut in the ruler position. So for example, if we're trying to do so after we split this array, we have a ruler stick of size 3. We don't want to accidentally do a cut of 5 on a stick that's shorter than it. So we just need a conditional here to make sure that the cut itself is within the stick length. If this is the case, we can do our cut. When we do our cut, we need to add the current length of the stick to the output. So n minus start, and then we also need to add the returned results from the remaining cuts. So the first ruler stick will go all the way from left all the way to the current cut, so C, and then the second ruler stick will start at C and go all the way to the end, which is the end position. Once we get that, we need to update out so it's equal to the minimum of out and the return result. And now at the end, we can return out. Just make sure that if out is currently equal to float.infinite, which will be the case if we get to the branches down here where no more cuts remain, and this loop will still execute. So we just want to catch that exception and return 0. So just a minor error in the conditional, make sure it does not equal the float.infinite. If you run that, it will pass the test cases, but it will not pass on LeetCode because it's far too inefficient of a solution. Okay, so the next solution is going to require us to make use of memoization. Memoization is a technique where we cache our results as we come up the tree. That way we can avoid repetitive work. Repetitive work you can see here is, for example, at this position right here. When we get down here, we're trying to find the optimal cut after we have an interval from 3 to 5. So you can see how this this path and this path is basically the same, but we're looking down it nonetheless. You can also see how, for example, if after this one right here, let me draw it out a little on the side here. If we did this first cut at position 1, and then just right after that, this first cut at position 1, where the interval was initially 0 to 7. After we do this cut, we will have 2 branches. One where the cut is going from 0 to 1, and another where the cut is going from 1 to 7. Now, coming down to this branch on the right here, if we were to do a cut at 3 next, notice what happens. Now,
we have a branch on the right going from 3 to 7. This branch right here. It doesn't really matter if we search down this tree once again, because we have already stored the result of that right over here. We don't need to do it again. And it's even more obvious visually. If we do a cut here, uh, once we do a cut here, it doesn't really matter that it needs to go through the tree on the right again, because the result here that we obtain will always be the same. Essentially, because of the intervals that we're dictating, the cut made by the 1 here does not affect the cuts made on the right-hand side after that cut of 3 is made. So we can essentially cache that and save ourselves a lot of work. Finally, to quickly go over the time complexity, this one's not that hard. Essentially, the time complexity is more or less dictated by our caching, where the cache is essentially storing every combination of the start and end pointer, which is dictated by our cuts. So every time we do a cut, we have essentially 2 new intervals. If we do every single combination, that will be a C squared space complexity, which would also transfer over to the time complexity. But actually, because we're doing this additional for loop in between where we're creating these branches over and over again, the actual time complexity would have to get multiplied by C once more. So the total time complexity is C cubed. Hopefully that made a little bit of sense. And yes, the space complexity is C squared. We store every single combination of cuts into the cache. So we actually do not need to rewrite our brute force solution or write a new solution at all. You can just modify it. And this is really what you should be doing anyways. You should write out the brute force first and then modify it and include the memoization. So let's create our dictionary up here, which will hold our cache. So after we calculate this result and get the output, we need to make sure we cache this into our mem. So mem at the interval, so start end is equal to out. And actually, we can move this statement up here and then return our cache. And to actually use our cache, we need an if statement up here where we check if this interval, we've seen it before. Then we can return what's already stored in our cache. And there we go. Let's just make sure that works. Great, and this should pass. Awesome. Okay, to just fix the time complexity up here, as I said, it should be C cubed and C squared. C squared because we store every single combination into our cache of start and end pointer, and C cubed because although the cache is cutting our time complexity down to C squared, we have this extra for loop inside our DFS. Okay, time to give you that follow-up question. I'm just kidding. I feel like this problem was hard enough, and I really don't know what a follow-up would be. Um, but hopefully you guys enjoyed. Just let me know if you like the new quality in the video. If there's any other thing you guys want to watch. I was thinking of introducing some Binance to the channel if you guys are up to it.